So good night, everybody. Can everybody hear me okay?
Yeah.
Yeah? That's fine. Okay. So tonight I'm going to be talking a bit about massive stars, what they are, why they are important, and mainly the title of the talk, how do you make one of them? Okay? So hopefully this is going to be you in about half an hour, right? Looking at starry night sky, right? And if you look there, how many of the stars do you think are massive stars? Well, the first question you might ask me is, what is a massive star? So, a massive star here, for the purpose of this talk, is anything that has a lot of mass. So we are talking about kilograms. It's not something that's just big. So you could have like a balloon, right, an air balloon, that's the size of this room, and it would be massive, but it wouldn't be massive in terms of having a lot of mass, right? So sometimes it is correlated to size. Sometimes things that have more mass are also bigger, but it's not always the case. But I'll give you some idea of what are massive stars just by talking you through this diagram. So here on the left-hand corner, you see our poor little Earth, right? Which is tiny in terms of size, but it has a very large mass. The Earth has 6 times 10 to the 24 kilograms, which is a 6 followed by 24 zeros, right? This is more kilograms in the Earth than grains of sand that exist in the whole of the beaches and in the whole of the deserts. That's a lot of kilograms. The Earth is very massive. But compared to the other planets in our solar system, so you have Neptune, Uranus, Saturn, and Jupiter. Jupiter is the most massive one. We could put 300 times the mass on Earth into Jupiter, right? So the Earth is not as massive as some other planets, but even those planets, they are nothing compared to the Sun. The Sun has 300,000 times the mass of the Earth, right? And even the Sun is sort of an average, mass star. It's not really massive. It's not one of the few. The really, really less massive stars are about a tenth of the solar mass. But you can really get stars that have a lot of mass, like 10 to the 31, 10 to the 32 kilograms. It's a huge amount of mass. You can fit hundreds of suns inside of them. And these are these 2 stars here that I'm going to be talking about. So they are called OB stars. We won't get into that. But if you want, you can also do it. Right? So these are stars with 100 mass of the sun. So that's what I just said. So massive stars are stars with 8 to 100 solar masses, more or less. Now, for every star that we see forming in the universe, if you form 100 stars, just like our sun, then you form only one star that's 30 solar masses. And on the top of that, stars like the sun live a lot longer. They live like 1,000 times longer than a massive star. So massive stars are around in the universe for a lot less time. This is still like a million years, right? But for a star, that's nothing. For the universe, that's nothing, right? So when you look at the sky or a random direction, you see on average 100,000 more stars like our sun than a star that's, say, 30 solar masses, right? However, a star with 30 solar masses emits a million times more light than a star like our sun. So if you look at any direction, most of the light you're seeing is still light from these very, very rare massive stars that there are in the universe. So they still dominate the light that comes to you, right? So we want to understand how a massive star forms. And to understand how a massive star forms, you have to understand how a star forms. And to understand how a star forms, you first have to know what a star is, right? So what is a star? So I think the life of a star can be pretty much resumed into a constant fight, which is the fight against gravity. So the star is constantly trying to fight gravity. So gravity is a force that acts on things that have mass, right? And we just said that stars have a lot of mass, and we're talking about massive stars that have even more mass. So this sounds sounds like an important force to talk about, right? So what the gravitational force is trying to do is to squeeze the star, compress it, right? So you want to squeeze and squeeze and squeeze. Now, we don't see stars squeezing and disappearing because of gravity. So something must be balancing it out. And it's balanced out by heat and pressure. And this heat and pressure come from something that releases a lot of energy that happens right into the core of the star, where it is the hottest bit of the star, which is something called nuclear fusion. Now, nuclear fusion is one of those things that are super simple and yet incredibly complicated. So I'm just going to give a very, very flash explanation of what nuclear fusion is. So this is my beautiful, realistic representation of an atom, right? So atoms are made of a nucleus, which is positively charged, and of a cloud of electrons, which are negatively charged. So let's just concentrate in the nucleus, just for sake of simplicity. So this positive charge is an electric charge. And if you have things that have the same charge, so if you have two positive charges, then they repel. They don't like each other, right? So that's what you see here. They hate each other. They don't want to get together at all. But then there's something funny. If you can manage, if you have enough energy to get those really close together, right? Then another force enters into action, which are the nuclear forces. And then they all of a sudden decide they love each other, they want to spend eternity together, and that's what we mean by nuclear fusion, is when you pretty much slam one nucleus into the other, and then you form a new nucleus that is the combination of the other two nuclei, right? Now there's something very funny about nuclear fusion. It is that if you take this nucleus that you had the result, the combining nucleus, and you weigh it, and you take the two nucleus separately before they were fused and you weigh it, then the combined nucleus is lighter than the two nuclei separated. So you have less mass in the combined one than you had before when they were separated. So it's basically like you start holding hands with somebody and suddenly you are lighter. So you don't have to go, and diet anymore. You just hug everybody and then suddenly you're like, so what's happening here? Where did this mass go? Right? So you might be familiar with this guy, showing the tongue. Nobody criticizes him for showing the tongue. Seriously. This equation, which you might have seen but don't know what it means. So I'll tell you what it means. So this is the energy mass equivalency. This means that if you take a little mass and you multiply by a constant, which is the c is the speed of light, which is basically a number that's very, very big. This is almost the number, right? Super large. Then you can create a certain amount of energy. So basically this is saying that I have mass, I can transform it into energy, right? For you to have an idea, if you take 1 kilogram of hydrogen and you fuse the hydrogen nuclei via nuclear fusion into helium, then you have energy for your house for the whole year for the next 10,000 years. I didn't spot the error there, so everybody just ignore it, right? It's perfect. Anyway, right, so that's what's happening in the inside of the star, right? You're taking this nuclei and you're fusing them together, and then a little portion of the mass is disappearing and is turning into energy, and this energy is emitted as light. So that's why stars shine, and that's what's helping in the fight against gravity, right? Now, different elements, different chemical elements, they have different amounts of the charge units, the positive charge. So hydrogen has 1, helium has 2, carbon has 6, nitrogen has 7, and so on. It could go out for the whole of the periodic table, right? Now, if you have something that has 2 positive charges, right, it has a stronger repulsion to something that is positively charged because it has more electric charge on, the force is proportional to the charge, so the more charge you have, the more you repulse one another. So what does this mean? It means that if you take 2 hydrogen and you try to mash them up together and fuse them, It's easier than to take, for example, 2 carbons which have 6 and fuse them together. Okay? So, to have this energy to slam the nuclei together, you have to have very, very high temperatures. And these high temperatures that make the slamming only can happen in the interior of massive stars. Only they have enough gravity to push and make things heat up enough to make the heavier elements, the elements that have more positive charge in their nucleus. So massive stars, they can create oxygen from carbon, they can create silicon from oxygen, they can create iron from silicon, and they end up with this iron nucleus just by fusing and fusing and fusing these atoms together, right? Now, there's a big problem when you get to iron, right? And the problem when you get to iron is that then the thing reverses. So you remember how I said that the nuclei separated, weighted more than the nuclei together? From all the elements from iron onwards, it's the opposite. It takes more energy for you to put them together than when they are separated. These are the elements that when you make nuclear fission, when you break them up, you actually release energy. So what does that mean? It means that once you have an iron core, there is no way you can produce energy to keep fighting gravity, right? What happens if you have no energy to keep fighting gravity? You go kaboom, right? Because what happens? You don't have any way to fight gravity, so gravity just collapses everything, right? And then in the center, you form either a black hole or a neutron star. And then a lot of energy that was stored by the gravity, the gravitational energy, suddenly turns into thermal energy. And everything explodes like a huge bomb, right? And when it goes this bomb off, that's what we call a supernova, okay? Now, supernova is incredibly energetic. So energetic that when the supernova goes off, the light it gives off can outshine an entire galaxy. So can you imagine a single little star going supernova shines more than millions of stars together? That's crazy, right? Okay, so this is a supernova. It's class A. And this is pretty beautiful. You can see the material is shedded outwards. And it's in this supernova that you can also build some of the heavier elements, heavier than iron. Because then you don't care, you have so much energy that you can just eat up energy. So you can just, even if it takes energy to put the nuclei together, it's fine. You have plenty of energy that was giving up. So what happens? It happens that this is the periodic table of elements, right? And basically everything that's in the blue rectangle, and these ones here, which all of this is made by massive stars, either during their life or during their death. All of this is produced by massive stars, either in supernovae or as they are doing the fusion in their nuclei. Now, these ones, the red ones here that I highlighted, those are the ones that you find in your body. So basically, none of you would be here if it wasn't for the massive stars that have produced lots of really nice elements to compose your body. So they are essential for life. And the black ones, they're also essential for life because they make part of your mobile phone. And we know that nowadays it's impossible to live without a mobile phone, so there you go. If you don't think you need for your life, then you at least need for mobile phones. Right. So how the massive star formation differ from the formation of other stars? Right? There must be a reason that I'm talking about massive star formation, or that I decided to study this topic, right? So, long time ago, in a molecular cloud, so molecular clouds are these huge clouds in the middle of the universe that have a lot of gas, and they are the stellar nurseries. Those are the places where stars form, right? And usually what you have this region where you have hundreds of solar masses, and this region doesn't have any stars yet. And if it has hundreds of solar masses, it has a lot of mass, right? So what happens? Gravity is winning because there is nothing to fight it. So it starts collapsing. So it starts collapsing and it starts collapsing and it starts collapsing. It loses gravitational energy. As it loses gravitational energy, the things in the center heat up because you're gaining them as thermal energy. And as you get thermal energy higher in the core, then in the core gets temperatures high enough so you can start this fusion process. Now for most stars, that's it. Like you started nuclear fusion and they say, yeah, fine, I'm formed as a star, I graduated, I'm just gonna go and live my happy star life, right? But it turns out that this happens even for the most massive stars when it's around 8 solar masses. But we see stars with 30 and 50 and 100 solar masses. So how do they get that massive? Why is this a problem to start with? Well, once you start fusion, I told you, we are releasing enormous amounts of energy. And if you start releasing enormous amounts of energy, then what happens to all the gas that's around? Basically, you start pushing it away with radiation. So you just have the radiation coming from your star, and you go poof, 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 and you start getting all the material that you were accreting onto yourself, that you were gaining mass from, away. So you're pushing all the material away, and you still have to find a way of increasing your mass. So this is the bubble nebula, and this is a little O star, and you can see all the material that it just pushed away because of the enormous amounts of radiation it's emitting, because of this fusion that's happening, right? So okay, we have to keep accreting mass somehow, gaining mass somehow. Maybe we can observe it. That would be the easy way, right? Right? But that's tricky. I'll tell you why it's tricky. First, because they're very, very far away. The molecular clouds that we know that are forming massive stars are like a kiloparsec away, which, if you don't understand, is this many meters away. It's very, very, very far away. And what's the problem with that? The problem with that is that if you take a picture, imagine that you're trying to see something in the end of the street with your phone, right? There's a person standing at the end of the street, and you take a photo of your phone. Click, right? And then you want to see if that person is smiling or has a sad face. And then you go there, and you zoom in, and then you discover that that person is only a pixel. And then there is no way you can see what's happening. And that's sort of what's happening with the massive stars. They're very, very, very far away. It's very hard for you to see what's happening in detail. And to make things easier, they are hiding, obviously, right? So they are playing peekaboo with us. And so this is the Rosette molecular cloud. So this is one of the places that star formation, massive star formation is going on. And this is a massive star forming, and you tell me, how is it accreting more mass? How is it gaining more mass? I can't see anything. There's a bunch of gas and dust in front, and it's very hot. And to make things worse, because they are so massive, it means that the force of gravity is stronger, which means that everything evolves much faster. So the period that they are forming is much smaller, much shorter than the low mass stars. So they are very rare, and it's very hard to see them at all. And yet, whenever we observe one, right, forming, or we think we observe one forming, there's another one. They are super rare, and yet, when you find one, you find another one, and sometimes another two, sometimes another three. So what's happening, right? So that's where my research comes in. So let's go to theory. Right? So we're trying to work here on step 2. Yeah. So anyway, so everything that accretes, that gains mass in the universe that we know, does so via what we call an accretion disk, which is this thing, which is basically just a disk where you're collapsing things, you're collapsing material inwards, right? And this star in the center, this is an artistic impression, it's not an astronomical photo. So this is just gaining more and more mass via this accretion disk. What does this mean? It means accretion disk, I can accrete more mass. I can get more massive. That's good, right? So what happens is that, so you have your star there, and this is my super realistic representation of the accretion disk. And you have the star in the middle, and then suddenly, boom, fusion starts in the center, and then it pushes all the material away. And then you can't accrete anymore because you don't have a disk. So you need a disk that doesn't blow up. How do you make a disk that doesn't blow up, right? So to make a disk that doesn't blow up, you need a disk that's denser, that has more material there, and that it's more concentrated. And the way to do that is by putting many stars together. Because if you put many stars together, each of them have a little mass. But their combined mass is very large, which means that they can attract a lot more material, right? And because they have a higher gravity, it also means that they flatten the disk more. So you get this disk that before was like water, you could push it away, and now it's like a stone wall. You can't completely push it away anymore. So you can keep the disk living for longer, which means that you can continue accreting. But to keep accreting, they have to have other stars helping them. They have to be lots of little stars holding hands and saying, we're going to get massive, but we're going to get massive together, right? So that's basically the punchline. So here's the recipe if you want to try it at home. So how do you make a massive star? You find a molecular cloud. You create a very dense region with a few hundred solar masses. You make sure that a few massive stars form in there, and they all have a common accretion disk, right? And then you let them cook until the desired mass is reached, and voila, massive stars. Yeah. So take-home messages from this talk is massive stars, they are rare, but they are very bright. They are the universe's great chemists, and a bit of what they produced is in me, is in you, and is in your mobile phones. And strength lies in numbers. If they didn't stick together, they probably wouldn't form. So that's it. And thanks, and have fun.